Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, today we're pleased to have Rick Kenyon here, who many of us know already. So today he's going to be talking about the double dimer model and how to see that it's conformally invariant using quaternions.
Thanks, David. So I want to start by talking about the dimer model. I mean, before I talk about the double dimer model, just to make sure everybody knows where we're starting. And I hope you all feel free to ask questions about anything. So dimer model is a model on it's a probability measure on the space of perfect matchings of a graph. Okay, so we're going to start with a graph, set of vertices and edges, and in general we're going to have a function on the edges, a weight function on the edges, so nu, and it's going to take positive real weights. And from this data, the space of perfect matching, so a perfect matching of the graph is just a set of edges which covers all the vertices exactly once. So M of G is a set of perfect matchings or dimer covers. Okay, so all right, so there's a perfect matching of my graph. And associated to the weight function, we can put a measure on the set of perfect matchings. This is G is a finite graph. M of G is a finite set. So let's define the measure mu. So on mu, a probability measure on M. So we want to define a random matching, and a random matching is each matching is weighted by the product of the edge weights it uses. Okay, so the probability of a matching M is going to be, proportional with some constant proportional to the product over the edges in the matching of the weight of that edge. So the weight of a matching is just the product of the edge weights, and the probability is proportional to that. And then the constant of proportionality is a partition function z. Right, so z is just going to be the sum over capital M of the weight of M. Right. So that's the dimer model, and just one. It's of course a very well studied model, which I've been working on it personally for 15 years. There's lots of interesting questions, which come up in the interesting question about the dimer model on large graphs. Okay, one thing I wanted to say, right, this is a good place for it, is that if you change the weight function, you don't necessarily change the measure. And in fact, if you take a vertex and you multiply all the edge weights there by a constant, then that's not going to affect the underlying measure. So if I take these weights, A, B, and C, and I multiply them all by some constant lambda, the measure doesn't change. Okay, why is that true?
Exactly one of those will be. So you can do it for several of them.
That's right. That's right. So this is called a gauge transformation. And I'll explain why it's called that transformation shortly.
So this relates to gauge that are in physics? Or
Yes. Yes.
Gauges?
Yes. It's called a gauge transformation. Maybe I'll. And Well, as you've all said, every perfect matching uses exactly one of these edges, so all perfect matchings get multiplied by lambda and when you do this. And so you get a lambda in the numerator and the lambda in the denominator. Those cancel, you get the same measure. And of course, you can do this at more than one edge, more than one vertex. All right. Well, the most important, I mean, the root of all computations in the dimer model is the theorem of Kastelein. Which was, I mean, the basic case was for the square grid, which was also proved by Temperley and Fisher in the 60s. Temperley, Fisher. So, I mean, they get credit also. But Kastelein proved the more general case. If you have a planar graph, it's possible to actually compute the partition function using a determinant. So, and I'm just going to let me just state it in the case of a bipartite graph, since it's a little bit easier. If G is bipartite and planar, then Z can be written as the determinant of a certain matrix, K, called the Kastelein matrix, which you construct from the graph. It's essentially a weighted adjacency matrix. So K, you know, here the graph is bipartite. 1, 2, 3. So there's two types of vertices, blacks and whites. And K is sort of the adjacency between the white vertices and the black vertices. So K of Wi, Bj is going to be, well, it's going to be the weight on the edge from Wi to Bj if there is an edge, right? And with a sign, otherwise it's going to be 0. What? And the sign? Yeah, so the trick is to figure out what the signs have to be. And, so the rule, one rule is that around each face, so you want to put some signs in, throw in some, sprinkle some signs down so that around each face, if the face is a multiple of 4, you have an odd number of signs, and otherwise you have an even number of signs. So, for example, this face is a square, so it has to have an odd number of minus signs. So I could put 1 there. This one is also a multiple of 4, so I could put 1 there. And this one is 6, so it's not a multiple of 4, so it has an even number of minus signs. So that would be an example of a way to put in the signs so that this theorem is true. Well, I should put in an absolute value sign here. So that's called a Kastelein weighting of the graph when you put in these signs. Okay, I'm not going to talk about that theorem today, but just to get the statements straight, that's the end. So, but the point is that because you can compute this partition function in a fairly simple way using determinants, even for very large graphs, large regular graphs, you have a good way to get a handle on the set of matchings, and that's why this model can be really, you can really work with this model in a fairly large generality. On the other hand, two important provisos are, well, the most important one is planarity. If it's not planar, then you're out of luck. There's no related theorem. If it's not bipartite, there is a more general version of this theorem, which uses Pfaffians. I'm not going to talk about that either. But bipartite is not really an important constraint for this theory. Okay, well, now let's talk about the double dimer model. Maybe I'll do it here. And this is double dimer model. This is the definition is very simple now. You're just going to take two independent dimer covers of a given graph. And that's it, right? So we're going to, but you can view it, you can of course draw these two dimers on top of one another. right? So there's a black dimer cover and a red dimer cover. When I draw them together, I get some loops. Every vertex has degree 2 now, and some doubled edges. So this is just, let me just say, probability measure is the product probability measure on 2 independent dimer covers of the same graph. Alternatively, you can think of it as a probability measure on edge configurations of a graph where an edge configuration consists of loops and doubled edges, or configurations of
You mean loops, you mean cycles.
cycles. Yeah. Is there a difference? Oh, okay. Yeah. Oh, you're right. So I'll call it cycles then. I'll probably call it loops later on, but cycles and doubled edges.
And only cycles of even type alone.
That's what you get.
That's right. In the bipartite case, you don't have to say that, but in the non-bipartite case, yes, it's more. That's important. So even length.
But if it's not bipartite and you just draw 2 independent dimer, yeah.
It'll still have even length, right? If it's non-bipartite,
even
every cycle, in a given cycle, every other edge is in one matching, and every other edge is in the other matching. Right.
So why only 2? Sample more than 2?
You can certainly sample more than 2, but this is the one we're going to consider here. All right. In this case, of course, the measure is just the usual measure. If you want to try to think about it in terms of loops and doubled edges, how should you assign a measure? I mean, what's the corresponding probability measure? Well, you take the product of the edges that you see, but then you have to, there's an extra factor of 2 for each edge, for each loop. So the probability of a configuration C is, so it's the product of all the edges in C as before, but then you get an extra factor times 2 to the number of cycles. But whereas a doubled edge does not count as a cycle, but every other cycle gives you factor 2. Right, because there's only one way. There's only one way to, cover with 2 dimers a doubled edge, whereas there's 2 ways to cover every other cycle. Okay. So that's the double dimer model, and not much else to say there. Well, so what are the questions which we want to ask about these models? Well, we want to consider, in probability or statistical mechanics, we're interested in the large graphs, like large periodic graphs, structures like the plane, the grid. What does a typical dimer model look like? What can we say about dimer models on a large graph, even an infinite graph? Can we define a limit of these measures in the infinite setting? Does that limit, depend on our sequence of approximations? Questions of this type. Many of which can be answered. I mean, if you have some particular question you want to ask, I'd be happy to tell you what is known about it. I mean, what I know. In a double dimer model, of course, we're going to get some, loops of various types. You might ask, how long is a typical loop? Questions of this type. What's the sort of fractal dimension of the loop, in the sense of, if you know a loop has diameter 1,000, how many, what should you expect its length to be? Of course, it was conjectured, a number of years ago that if you take the square grid on square grid Z2, you scale by epsilon, so that the mesh size is epsilon. You take a double dimer model. I'm not going to attempt to draw it here. And you look at the long loops. These should somehow, in the limit as epsilon goes to 0, these should converge to some nice loop fractal loop process, which has something to do with SLE4. So it's possible to measure the dimension of these loops, long loops, and it turns out to be the correct dimension for SLE4, which is 3/2, 1.5. And various other quantities you can measure about these loops all seem to point to SLE4 as being the scaling limit. So I'm not going to say what SLE4 is. Probably many of you know more than I about what that is. But
What's the process? We took this random two things, we look on the cycle, what we're fixing for the cycle, its length.
yeah, well, okay, so, right. Here's a simple question. I mean, here's a simple setup. I mean, let's take an annulus and look at and condition on having a cycle which goes around the annulus. Okay, so then you have at least one long cycle, and you can measure its length, its properties. Where does it go?
No, the initial dimer model with one matching on the grid correspond to some SLE?
Well, there's no, I mean, how do you define a path from a single dimer model? I mean, there are various ways to do it, but I want to study this particular model. I mean, there are ways to define it's related to the spanning tree process, for example. I mean, it's in bijection with the spanning tree process where you get SLE2. That was proved by Lawler, Schramm, and Werner. So a single dimer model does have some conformal invariant properties. So that's a sort of an old result. But starting from me, yeah. I mean, I proved this conformal invariance of certain properties of the double dimer model, in particular this height function, which I don't want to really talk about right now. So there's some convergence to the Gaussian free field. And then Lawler, Schramm, Werner proved that the spanning tree converges to the SLE2 and the SLE8, depending on which path you're. So those are all parts in this random domino tiling model, not random dimer model on the square grid. But this one has been more elusive. I mean, the SLE4 has been more elusive for various reasons. I'm certainly not going to prove that today, but I want to at least indicate how you can show that these paths are actually conformally invariant.
But this was already proved.
What was already proved?
It's SLE4.
No, this is a conjecture. Yeah. Do I need to write some words down here? No, I'll just leave it like that. Okay.
Example of actual random process that gives this double dimer distribution.
An actual random process? No. No. As far as we know, there's no sort of. I mean, how do you find the next edge? Not in any simple way. That's right. Right. If we had something like that, then it might be easier to actually prove. But I mean, for example, for the SLE2, the branch in the spanning tree, there is a way to generate it. But okay. Well, so this talk is really not about continuous objects. It's about combinatorics. And so I want to, I'm not going to try to, anyway. I want to introduce some non-commutative variables in this situation. And the advantage is that we can actually compute some sort of topological quantities about where these loops go, which we can't do with just commuting variables. So, and I could just say, replace the edge weight function, which was taking real values up to this point, with some quaternions. But I think I want to sort of think about it in terms of two-dimensional vector spaces and connections on a graph, because this is, in some sense, more geometric information. So let me talk about bundles on graphs. So vector bundles. And I think this is a sort of useful viewpoint because it's more general than just applying to this model. So what's a vector bundle on a graph? Well, I'm just going to start with a vector space, V, a vector, W, a vector space. And if I have a graph, I'm going to associate to every vertex a copy of W. So W, V, 1, W2, and so on. It's just an isomorphic copy of that vector space. And for each edge, I want to define an isomorphism between the corresponding vector spaces. I want to be able to transport vectors sitting at one vertex to a vector sitting at another vertex. So for each edge here, I'm going to have an isomorphism phi1, 2. Phi1, 2 goes from W1 to W2. So it's a directed object. If I go in the reverse direction, I'm just going to take the inverse of that isomorphism. So that's all a vector bundle is. Well, sorry, let me get the terminology right. Once I've assigned a vector space to each vertex, that is a vector bundle. But the choices of isomorphism, that's called a connection. So the set of phi ij is a connection. That's the connection in the same sense as differential geometry on the bundle. So this is I said that in words, but I didn't say that phi. If I do the edge in the reverse direction, it's the same as the inverse of the isomorphism in the forward direction. An isomorphism. So that's called a connection on the bundle. And in this talk, we're only going to need to talk about two-dimensional bundles. And the connections are therefore going to be two isomorphisms between two-dimensional vector spaces. If we choose a basis for each vector space, then I can represent these just by 2x2 matrices. And maybe you know that quaternions can be represented as 2x2 matrices, the rotations of the three-sphere. But so you can think about it in those terms. Complex matrices, yes. These are in general complex vector spaces. All right, so these phis are called parallel transport, these isomorphisms. So phi ij is the parallel transport. Parallel transport of vectors from vertex 1 to... So what situation is this natural? Suppose that our graph comes embedded on a surface or in some Riemannian manifold, right? So then, in particular, if we're on imagine a graph on a sphere, and maybe the edges are geodesic segments on the sphere, right? So then at each vertex you have a tangent bundle on the sphere, and right. So vectors in that tangent bundle. If you want to identify the vectors here, you want to transport the vectors here to there. You need some isomorphism between the corresponding things, and the natural one coming from the Riemannian metric is called the Levi-Civita connection, which essentially just you slide the vectors along the curve using the always maintaining the same angle with the curve, right? And that gives you a way to identify the tangent space here with the tangent space there. So that's an example where this setting naturally rises. Well, of course, just like in this previous setting, there's a notion of gauge equivalence. Which is essentially just a base change. If we so gauge if we think of this of having particular basis for every vector space so that we represent these things as matrices, then doing a base change in one of the vector spaces will just correspond to pre or post multiplication of the parallel transports by some matrix. So if we've got parallel transports phi1, phi2, phi3, and then we change this base, the base here by multiplication by m, there's some base change map, and it's going to be pre-multiplication of the parallel transports by that map. So at a given vertex, you're free to pre-multiply by a matrix for the outgoing parallel transports. So that's called a gauge transformation. All right. Now, that's all fine and dandy, but what relevance is it for our model? All right. Well, so how should we redefine our probability measure when we have a connection? So how to define. So now I'm going to stick with the double dimer model. Double dimer. How to define the probability measure. Well, so now we've got, on our graph, we've got a collection of loops and doubled edges. Well, every time we have a loop, we have an associated monodromy, which is you start at a point on the loop and you compose the parallel transports around that loop. And when you come back to the place you started, you don't necessarily get the identity, right? You get some non-trivial map from that vector space to itself. And while the trace of the monodromy is the relevant quantity. So we're going to define the probability, the measure of a configuration C, where C is a double dimer configuration. C, well, a double dimer configuration. It's going to be, well, again, we're going to still have our underlying weight function on the edges. So E in C, that's a nu of E. But then we're going to have the product over all cycles. We're going to take the trace of the monodromy. By the monodromy, I mean the composition of the parallel transports around that loop. Right. Well, why doesn't it matter where I start? Well, suppose I started here instead. It's just conjugation, right? So I go here, take this product, and then I go back. And so that's just conjugating, and trace is invariant under conjugation. So it doesn't matter where I start. Let's see. All right, that's the definition. Oh, well, 1 over partition function.
So this is a new measure.
It's a new measure, right?
More complicated.
More complicated. Well, it's more complicated, but I've got more parameters to deal with. So more powerful. If only I could evaluate this measure in some way, right? And theorem is that, yes, I can indeed. There's an analog of Kastelein's theorem in this setting. Which is that the partition, well, let's just do the partition function. Well, it's going to be the determinant, well, the Q determinant of a certain matrix. Let's call it K. Let's call it K again. K, well, K now depends on not just their weight function, but on the connection. So how should I denote that? K depends on our connection, capital Phi. Capital Phi is the set of all parallel transports. Well, sorry, let me see. When, let's not forget the hypothesis. When we have a rank 2 bundle, so a 2-dimensional vector space, when W is dimension 2, and phi, all the phis are in SL2C, so determinant 1. Right.
Does this mean anything about the graph, like the planar? Or
Yes. Oh, yes. Other. And G is bipartite and planar. See, I state the conclusion first, and then I state the hypotheses later. Of course, I didn't tell you what K is, but so I wouldn't have been able to define K except in this case. But then theorem.
What is Q det, K of V?
Yes. So that'll take at least a few seconds to describe. Well, what is K? Let me tell you about K. That's the easy one. K is just like the adjacency matrix, the kastelein matrix from before, with the weights, except that each edge weight now gets multiplied by the corresponding matrix. So K phi of Wij is going to be plus or minus the same signs. Then there's going to be the edge weight. And oh, okay. I'll do it over here. So K Wij is going to be plus or minus the edge weight times the parallel transport from I to j, from Wij. And, well, K is now going to be an n by n matrix where n is the total number of vertices, so both the white and the black vertex. So maybe I shouldn't distinguish between white and black here. Let me just say Vi and Vj. Is that going to be a problem? It's the weight from Vi to Vj, the parallel transport from Vi to Vj. So it contains a term with phi and a term with phi inverse, and it's going to be 0 if they're not adjacent. So here phi is going from Vi to Vj, and 0 if not Vi is not adjacent to Vj. And the signs are again determined by kastelein condition as before. Same kastelein condition. What is that? It's an it's an isomorphism between the vector spaces. So maybe what we should do is, well, see, part of the definition of Q det is I'm going to tell you what these objects are. Well, but if you like, you can just think of choosing a basis for each vector space. Then this is an element of SL2C. Yes.
And the monotony is not trivial, and then it doesn't matter on which way I go.
Yeah, that's a good point. Thank you for that question. Forgot to mention that. Well, doesn't the monodromy depend on the direction of the cycle? After all, I'm composing some non-commutative objects.
So it's moving in place, no?
What?
So it's the inverse.
Well, if I have the trace of a 2 by 2 matrix, A, B, C, D, it's the same as the trace of the inverse, D, A minus B minus C.
If it's in SL.
If it's in SL2C. And if I multiply by the product of, So indeed, it doesn't depend on the orientation of the cycle. Oh, another thing you might point out is that this definition, suppose that all of our parallel transports are trivial. Suppose they're all represented by the matrix 1, 0, 0, 1. Then what's the trace? Trace of the monodromy is the trace of the identity matrix, which is 2. So we get a factor of 2 for each cycle, which generalizes the previous definition. Okay, any other questions about Okay, so now I have to define what Q det is. Well, this is something which, so this is a matrix now whose entries are in non-commuting variables.
My question was, I'm still sticking
That's
at
fine.
that point. So the matrix itself can depend on the choice, but because it calculates the partition function, which is independent of the choices, then finally you will get something which will be independent of the choice.
That's correct. The matrix itself.
That can be done.
Yeah, well, I mean, the matrix doesn't see the cycles. It's just the matrix is just the actual entries on the edges. Each edge, right? I mean, this is the matrix from VI to VJ, which takes that
so
orientation.
it's just an edge. Okay, I
Right.
know it's the path.
Right.
Okay, great.
Well, so this is a matrix now with entries in SL2C, and well, the QDET. This is. I'm not sure who this is due to. This notion is due to, but I mean, you can read about it in this book of Mehta on random matrices. That's where I learned about it. So you. K has a particular property which is, I don't know, I'm hesitating between giving the theorem or the definition first. But let me try to give the definition first, all right? So if K is a matrix with entries in GL2C, and K is self-dual, which means, i.e., Kij is Kji dual. That is, ABCD dual equals dA minus B minus C. So this, if the entries are in SL2C, this is just the inverse, but in general it's the determinant times the inverse. Then QDET of K, well, is defined as follows. So you take the sum over, this is an n by n matrix, take sum over the permutations. It's just the same as the usual definition, K1 sigma 1, Kn sigma n, except that you have to permute these guys in a particular. You have to compose these entries in a particular order, and that order is going to depend on sigma. So how do I denote that? So by this I mean, okay, take the product. So the order here depends on sigma, on which permutation you're currently evaluating. All right? And so now I have to tell you what order to take. And the thing is that you have some freedom, but if two permutations if sigma and sigma prime have the same cycle structure, but except that some of the cycles are reversed, then the corresponding elements should appear in the same order in this product. I mean, so, sorry, let me say it this way. So the order is chosen so that elements in the same cycle of sigma appear consecutively. So that cycles of sigma appear consecutively. And I'll give an example. And I'll tell, well.
Wait, so
same if you reverse the cycle?
Just a minute. Just a minute. What I should have said is that if each cycle appears in a contiguous fashion in this product, and if you're if you have two permutations with the same cycle structure, then their individual cycles appear in the same order in this product. So if here's my cycle decomposition of sigma, then in K, I put all these guys first. K1 sigma 1, 1 sigma 1, etc. And then after I've taken the product of those, then I go to the next cycle, then I go to the next cycle. Okay, so the advantage of this is if you have another permutation, sigma prime, with the same cycle structure, except this one goes in the reverse order, for example. When you add this term to the corresponding term here, you can factor out the initial part, and you get the monodromy in this way plus the monodromy in that way, which is a scalar quantity. So the important factor we're going to use is that. Okay. Well, do you understand this part? For a given permutation, I decompose it into its cycle structure, and then the corresponding product, I go through the. Okay, so if sigma, I need a new color or something.
You can put the order of the cycles you can put in different ways.
That's right.
So inside the cycle you can represent it.
Inside the cycle you can do a cyclic rotation.
Rotate, right.
That's right. So if sigma is, x1 through xk1, x. I can't even write. Right. If sigma equals 1, 2, 3, 4, 5, 6, 7, and so on, right? Then the term is going to be k, 1, 2, k 2, 3, k 3, 1 times k 4, 5, etc. K 7, 4.
These brackets, it's not commutative, but it's associative, so it doesn't matter. It's still it's.
This is so far. This is just a way to define the corresponding term here.
Okay.
And of course, I've got some choice involved because sigma can be represented, in cyclic where I'm just going to choose one of those representations for each sigma. All right. Now, suppose that sigma prime looks the same, except that this cycle is reversed. 3, 2, 1, 4, 5, 6, 7, blah, blah, blah. Okay. What happens when I add these two guys together times the rest? Well, everything else stays the same, but these two guys, these guys are 2 by 2 matrices. When I add them up, when I take the product, rather, what happens if I take the product in the reverse order? I get the inverse. Or rather, I get the dual matrix. And when I take a matrix and I add it to its dual matrix, what do I get? If I take A, B, C, D plus D minus B minus C, A, I get 2 times the trace. I get the trace times the identity. I get A plus D times the identity matrix. So you see, this factor now is just a scalar. Okay. So what this comes out to be, so independent of the choices I made here about the cyclic rotation, or if I flip these guys around, I'm going to get a product of scalars out. And so that's that product of scalars is the definition of the Q determinant. So if you like, it's the sum over cycle decompositions. Sorry?
Now will come the theorem which is described in a different way.
Yes, I'm going to tell you a theorem. This is not the theorem. This is just a definition so far. cycle decompositions of sigma. So, sorry, this is a sum over. I'm just trying, well, okay, maybe I don't need to restate what I just said, because that will. Do I need to restate what I just said?
No, but you, we believe you. It doesn't matter how you.
Okay, just believe that for now. Let me write down the statement of the theorem, and then we can discuss the definition. That's right. So the theorem, and this is due to meta, is that the Q determinant of K, if K is self-dual, is just it's a determinant, really what it is going to be the Pfaffian of a certain matrix Z times K star. Well, if this is an n by n matrix, I can make a 2n by 2n matrix by replacing each 2 by 2 block of entries with those entries itself. Okay, and this is not the same Z as you've seen before, so maybe I'll call it something else. V, no. Okay, I even forgot what that letter is called. Zeta? No. Xi? Xi, okay. So Xi is this matrix of 2 by 2 blocks, 0, 1, minus 1, 0, 0, 1, minus 1, 0. And everything else is 0.
So this is actually this is to look at the
C divided by
C bar.
conjugate.
Yeah. That's coming out, don't worry. Okay, so C, yeah, okay. Maybe that's a bad letter, but anyway, it's just this matrix which multiplies by this diagonal matrix of, oops, I missed, 2 by 2 blocks. Well, the amazing thing is you take one of these self-dual matrices, you multiply by this, and you get an anti-symmetric matrix. It has a Pfaffian. That's the determinant. That's the Q determinant. Okay. Of course, I could have given this as the definition of the Q determinant, but I mean, I need that interpretation over there to give some meaning to the determinant. Alrighty. So, well, this is great because this means that using just linear algebra here, we can actually compute our new partition function, right? The new partition function, our matrix K, our kastelein matrix, is self-dual by construction, and now we can actually compute things with it. Should I? Do people want to ask questions anymore? Do you want to see an example? Well, here's a baby example, just for. Well, of course. Probably very useless example, but suppose my graph is this, right? Maybe it's worth just doing this example. So we've got 4 matrices, 2 by 2 matrices. Let's call them A, B, C, D. Then I construct this matrix, capital K. Well, there's 4 vertices, right? Let's call them 1, 2, 3, and 4. It's a bipartite graph, so these guys are all 0. 1 to 3 is A. I'm going to have to put in a minus sign because there's a kastelein condition. 1 to 3, 1 to 4 is minus D. Sorry, it's minus D inverse. 2 to 3 is minus B, is B inverse, and that's C. So maybe I should just, it doesn't matter. And the corresponding thing down here with the inverses. Okay, so the claim is that if you write out the little 2 by 2 matrices here and compute the Q determinant, you take You multiply by C, you take the FAFI, and then you'll get, what will you get? So Q det of K, well, it's just some function of these matrix entries, but it turns out to be trace of A, B, C, D plus, well, that's one double dimer configuration looks like this. The other one has these double edges, or the other one has those double edges. Each of those contribute 1, so I get 2. Sorry? Yeah, so that's the matrix which you get from the original kastelein matrix by replacing each SL2C matrix by a 2x2 block of real complex numbers. Huh?
The 2 by 2 are always like this? No.
No, the original, the identical thing, you just remove some of the parentheses.
Right, so if this is K, then K, in this case, 8 by 8. The 2n by 2n one is going to look like 0. It's going to be zeros, and then it's going to be A1, A2, A3, A4, and so on. All right, now graphs on surfaces. In the end, we're interested in a planar graph, right? Well, maybe we're interested in a graph. So we're going to say that, well, or maybe we have a graph on a torus, right? That's a sort of a typical setting. Is you want to approximate the square grid with a n by n grid with periodic boundary conditions. Well, so in this case, it's natural to look at flat connections. So a flat connection, that's one where there's no monodromy around topologically trivial loops. So it's a connection which, if you look at the monodromy around a loop, you get the identity unless the loop is a topologically non-trivial one. And these are the ones which we're going to be interested in with trivial monodromy, trivial loops around topologically trivial loops. So for example, in the torus, really there's only, if you have a flat connection, then around any loop you're going to get the identity, but when you go around the torus this way or this way, you get a matrix. But if you take two different paths around, the monodromy is just going to be the conjugate to each other. So in fact, for the torus, there's a flat connection on the torus. There's really only two matrices you need to give, one for the horizontal direction, one for the vertical direction. There's only a finite dimensional space of flat connections. Another setting is if you just have a graph like an annulus, right? What's a flat connection on an annulus? Well, if you have a loop which goes around the annulus, you get a non-trivial, potentially non-trivial matrix. But if you have two loops which go around, then the monodromy around here is going to be conjugate to the monodromy around there, because if I go around this way and then go back and around this way, that's a topologically trivial loop. It gives me the identity. So there's only, for an annulus, there's only one matrix if you have a flat connection. One sort of important matrix, which is the one which you get by going around. For a torus, there's two, and you can imagine how it works for more general settings. So in the case of a flat connection, our theorem can be restated, and I'm just about done here, in the following setting, in the following way. This is just a restatement of the theorem. So if G is embedded on a surface, and capital phi, our connection is a flat connection, then what can we say about our partition function for our double dimer model? Right, now it's going to be this is a sum over all configurations, C. Now, again, we still have the product, but now we're only going to get the product over non-trivial cycles. Non-trivial, by that I mean topologically non-trivial cycles of the, the trace of the monodromy.
But there are many non-trivial cycles.
Potentially many of those.
Just one from each.
No. What do you mean? No, yeah, so every cycle, we have to take the product of the monodromy over every topologically non-trivial cycle. But, for example, if you have a graph on an annulus, there may be 13 cycles around, and we're going to get that trace of that matrix to the power 13. Because every cycle contributes the trace of its monodromy. All those monodromies are the same.
Wait, what do you mean 13? There will be many in between 13, I don't know. You can go with zigzag. No, I mean,
So here's our annulus.
yeah.
Right? Our typical configuration can have a bunch of cycles which wind around. The cycles which don't wind around, they're just one. Yeah, I mean,
All the cycles that are around contribute the same thing.
they all contribute the same amount because it's a flat connection essentially. The monodromies for cycles which are parallel to each other are conjugate to each other, so they contribute the same trace. What?
No. I withdraw this.
So this is just a restatement of the theorem. I mean, it's not even a theorem. It's just a sort of a trivial simplification of the previous theorem. But the point is that here, in this setting, when we've got our connection depends on a finite number of matrices, right? If we've got a sort of genus G surface, we've got two G matrices, and this thing, Z, is just going to be a polynomial function of the entries in that finite number of matrices. So note, Z is a polynomial function in the matrix entries. It's not just any function, it's a function which is invariant under gauge transformation, under gauge equivalence. And there's a theorem about these kind of functions, which is also not due to me, it's due to Fock and Goncharov. It's a beautiful theorem. Which says that these, well, okay, so let's let curly V be, so we're going to start with the surface, and let's let the sigma be a surface. Let curly V be the vector space generated by product of the trace of the monodromy over all flat connections. How do I say that? Let B be a surface and phi a flat connection on sigma, or maybe it's a graph. No, well, flat connection on sigma. So let's let V be the vector space generated by, is an infinite dimensional vector space well, sorry, let me say it this way. It's going to be the vector space of polynomial functions of the matrix entries of phi. Vector space of polynomial functions of the individual phis, which are invariant under gauge transformation. This is something which is, and because we're dealing with flat connections, this is, it's an infinite dimensional vector space, but it's finite in each degree. If you fix the degree of the polynomial, there's only a finite dimensional vector space. And the theorem is that this Do you understand what I'm saying here? I have a flat connection. It depends on some matrices. And I look at the polynomial functions of the matrix entries. For example, the trace is that of, well.
So this theorem by whom?
This is a theorem by Fock and Goncharov. This is just a definition so far. V is actually generated by the product of the traces of the monodromies for simple closed curves. So V has a basis, well, is generated by product of the trace of the monodromy over all monodromy of gamma, where gamma is a in X, where X, so on your surface, whatever it is, you take all possible simple closed curve systems, which are, so simple closed curves, sets of simple closed curves which are disjoint from each other. You each time you have a simple closed curve system, you look at the trace of the monodromy. This is a polynomial function. You take the product over all curves in your, so X is a sort of a lamination on your surface of a finite set of curves. As X varies over sets of simple closed curves, disjoint, pairwise disjoint, simple closed curves. So this is a little bit, I'll give it the sort of basic example in a sec on sigma. Well, not only generated by, but actually these guys form a basis. That's what I should have said. Has a basis. Basis, colon. And moreover, there's actually an inner product on this space which turns into a Hilbert space in which these guys are essentially orthogonal. In fact, well, as long as the surface has a boundary, if sigma has a boundary, non-empty boundary, there's a Hilbert space completion for which in which these guys are actually orthogonal to each other. There is an identification of, well, what should I say? A V with, I mean, there's a completion. A natural inner product. Making, well, V into a Hilbert space. Well, I mean, its closure is a Hilbert space. So in particular, you can extract various things using that inner product. Well, what does that have to do with us? Why do we care? So here's a very simple case. Let's do this is sort of a baby case, which is trivial. But suppose we have an annulus, all right? Our double dimer model has a certain number of loops around here. And our partition function, what's our partition function? Well, it's the sum, and then...
The SLE4 prediction give you the distribution of the number of loops? Or?
No. No, but this theorem actually does. So what is the partition function? It's the sum, well, there's some weights, times, well, trace of m to the power k when we have, if k loops. So it's the sum over configurations of k of c. So maybe I should just say size of c, where size of c is just the number of loops which go around, right? If I hand you a function like this, it doesn't, with some coefficients, a function of m, you can extract, of course, the coefficient of those configurations which have 13 loops, right? So this is of course let's let this be some variable z, which we can vary, right? So this is, well, maybe it's just t, right? So this is just some polynomial in t, and we know how to extract the coefficient of t to the 13th from a polynomial, right? Just some integral, right? But that coefficient has a probabilistic meaning. It's the set of configurations which have 13 loops going around the annulus. And so the theorem, which over here says that we can do this in a much more general setting of.
So this give you actually, you can actually compute things using it?
Yes. It's hard. And just to close, and I'm sorry I'm way over time, but suppose that I'm on the region in the plane, and I want to study the double dimer model on, say, the upper half plane. Now I'm going to pick some faces, and now I'm going to ask, what's the probability that my configuration has a loop which goes like this, another loop which goes like that, right? This is something which this theorem will say I can compute the probability of this using this technology. I mean, I can compare this probability with the probability of any other sort of topological configuration of loops. In particular, that allows me to compute the probability that a loop does some particular thing. And these things you can compute in terms of the actual Green's function on the lattice. I mean, it's the same, everything boils down to the Green's function for the simple random walk on that thing, doing some complicated integral with products of Green's functions. And so these probabilities are all conformally invariant. If you do it in a different domain, the Green's function is conformally invariant, so these probabilities all turn out to be conformally invariant quantities. So that's where you get the conformal invariance of the double dimer loops. So I'll stop. Thanks.
About the final statement. So the calculation is exact at the level of the lattice, and you only need the, so for the green level.
Well, at the lattice level, you can do an exact calculation of these probabilities. You want to show that in the limit, as epsilon goes to 0, these things go through. That's a little bit non-trivial. But so what you show instead is that the ratio of the partition function with these, for any particular flat connection to the original partition function, is conformally invariant in the limit. But yes, I mean, there's some non-trivial step which I don't have time to talk about here. But you know, the combinatorial part is, I think I presented essentially all the arguments here. Nothing left out there. Well, I mean, of course I didn't prove this theorem, but.
This is a recent theorem?
2003. So fairly recent.
It's not the same famous folk, it's a young folk.
Mitrov is from Brown, right?
Goncharov is from Brown, Fogg, Vladimir Fogg.
Or maybe it is the
I think it may be the famous Fogg, yeah. The famous. It's a representation. It's a theorem in representation theory. I mean, the proof uses representation theory of SL2C. It's not actually that hard. I could pretend it in 20 minutes, but you have to know. I mean, it's good to know a little representation theory.